All right, we're back. Now we're going to add the boundary conditions, okay? All right. So all boundary conditions, whether they're forces or constraints, or we call them boundary conditions, and we put them in a special type of collector called a load collector. Okay, so we're going to create that now. Again, it's like a layer. Okay, so we're going to create, and here you're going to see load collector. So again, there's reasons when we have more complicated models, we might have hundreds of boundary conditions, hundreds of loads on different components, and it might be easier to organize them on different layers. This is a simple model, so we can just use one, but we still have to create it, so we're going to make a single load collector, and we're going to just call it BCs, okay? Sometimes I put the forces on one and then the constraints on another, but I'll just keep it simple and make one here, okay? All right. So that's active. You can see it's highlighted. So if I create forces or constraints, it's going to stick it into that collector. All right. So let's first do the constraints. Let's constrain the two lower nodes on the lower wing. So that is going to be all that stuff, defining loads and whatnot, is in this radio button called analysis. So go there, click on analysis, and here you can see we have constraints. So let's do that. We're going to click on constraints. That's going to make in Nastran or OptiStruct what we call an SPC, a single point constraint. And you can check all 6 of these, but really the rotational degrees of freedom don't really do much for these types of elements. They only support translational. So you just need to constrain 1, 2, and 3. That's the translation in the X, translation in the Y, and translation in the Z. Degrees of freedom 4, 5, and 6 are the rotations about the X, Y, and Z axes respectively. Okay, so we don't really need to do this, but if you click them, it's fine. It works. And then we're going to pick the nodes. So we're going to pick this node and this node, and then create. And you can see it makes these little triangles where it shows it as 1, 2, 3, and that means that degrees of freedom 1, 2, and 3 are constrained at both of those. Good. All right. So we've got the constraints. Those points are fixed. All right. So now we've just got to apply the forces. So again, under analysis, you'll see we have a little block here called forces. We're going to click on that. And that again kind of makes sense. We're going to pick nodes and we're going to specify a vector, right? So let's first put the lift load on here. So I'm going to pick that node. And it's going to go in the Y direction. So I'm going to change this to Y-axis. It's already there, I guess. And the magnitude to the 1550. And when I hit create, it makes a little arrow, and that is my lift force. And now let's do the drag force. The drag force is 750. Oops, not 755, 750. And it acts in the X direction. If you wanted to go in the negative X direction, you would just change the magnitude to a negative number. We have to click on that same node again, and then we're going to create it. And there you go. You can see that force there. Okay. Oh, I should mention how I scroll around and whatnot. So, okay, I have a 3D mouse, so I do it usually with 3D mouse. But you're probably used to this. Like you can do, is it control? Okay, so if you do control and the left mouse button, you can rotate. Control. Oops. If you do control and the middle mouse button, that's kind of useful. You can like draw like a little zoomy window. If you just do the middle mouse button, it doesn't do anything. Okay. If you do control and then I have like one of those like roller middle buttons, you can zoom in and out. And then the last one is if you do control and the right mouse button, you can pan, right? And those things are up here as well. You can go back and reset to the XY view or the YX view or whatever, right? So let's go back, and here we are. Okay. Probably if you wanted, you can pause the video and fool around with those things. It's not a bad idea. I should have probably started with that. Okay. All right. So now we've got the forces, the boundary conditions, the constraints. So it looks like we're ready to solve, right? But in fact, we're not quite ready to solve. We still have to define what's called a load step. So this is going to say what boundary conditions, and what type of analysis we're going to run. So in this class, we're almost only going to run linear static analyses, but you can also do modal analyses, dynamic response analyses, thermal analyses, nonlinear analyses, all these sorts of things. And there are different types of load steps because that's what tells it what type of solver you use, okay? So it might seem like we're ready to go here, but actually we do need to give OptiStruct a little more information, okay? And that's going to be the load step information, okay? So again, we're going to go into the model panel here on the left, right click, and create a load step. So down here you'll see load step. So I'm going to create that. And let's just give it a name, and we're going to call it lift drag. Okay. You could have different types of forces on here depending upon the situation. Maybe it's doing a roll maneuver or a crash thing, and you know what I mean, right? So you could have multiple load steps as well, even if they are all linear static analyses. But we'll just have one. And if we click on that, oh, I have to create it first. I'm sorry. Let's hit return. Okay. Now when I click on it, you'll see I have this some of the options for the load step. Okay. So the first thing I want to do is say what type of an analysis it is. So it's not going to be a generic analysis. It's going to be a linear static way up here. It's the first one. It's solver 101. Then there's lots of these other options, but the two that you always have to do is what load collector has the SPCs, where it's fixed, and what load collector has the forces or the loads. So that's what we're going to do here. So where the SPCs, we're going to click on here and then select the load collector where the SPCs are. So that's our BC's load collector. So there they are. And we'll have to do the same thing for loads. So it's the same load collector. Like I said, it could be different ones, but we'll have the same one. So there we go. So now that says, okay, I'm going to do an analysis on this model. It's going to be a linear static analysis, and I'm going to use the SPCs on load collector BCs and the loads, the forces that are also defined on that same load collector. All right. And the last thing we're going to do, just because we want to see the forces, it doesn't default write these out. We're going to actually have the analysis explicitly write out the forces in each one of these elements. Okay. By default, it actually just writes out the stresses, but we want to see the actual forces in each element. Okay. So to do that, we're going to scroll down here a little bit, and down here somewhere it should say output. Somewhere it should say output. Wait, where? I'm probably missing it. Oh, there it is, output. Okay, see there's output. And you click on that, and that'll open up a bunch of different options. So you can output the accelerations, the composite failure, element damage, all that sort of stuff. Most of them don't have any meaning in a simple model like this, but we do want to write the element forces, which is this EL force, L force. So that means element forces, not the force, right? So we click on that, and you can pretty much stick with the default values, right? There's like other parameters here, like formats and all that sort of stuff, but we'll just click on that and go with the default values for now, okay? And there we go. So we're good. All right. So now we're ready to solve, okay? So now we should be good to solve. Let's save it again. And now I'm going to go run it. Again, this is going to be under analysis, and we can just simply click OptiStruct, and that's going to take, it's going to write an input file, strut2.fem, which is indicated right here. You can change where that is or give it a new name, but it's going to write out an input file, and then it's going to take that input file and send it to the solver, OptiStruct. Okay? And it's going to do an analysis and all that sort of stuff. So you can just hit OptiStruct there, and you should see, the solver window pop up. It happened really quick in this one. Analysis completed, so it worked. I didn't get any errors. It's all good. So now we can go look at the results, okay? So you can click results here, and this will start Hyperview, which is like the post processor. So I'm going to do that, and it'll probably start that somewhere off window. So let me do that a little bit. Let me get it so you can see the whole thing. So it's a new program. Come on, you can do it. All right. So here it is. So this is Hyperview. You can see here's the truss. It's like in a different perspective. It's laying down. If you want to look at it dead on like we did before, we'll click this YX view. So it's looking down the Z-axis. And there's our model. Okay, so I don't see any results yet, but we can do this. So we're going to click on this little button here, which, you know, what type of results do you want to display graphically on the screen? So I'm going to click on that. And there's a bunch of different ones, like you can look at the displacements, but let's not do that. Let's look at the element forces first, right? So I'm going to pick 1D element forces. And if you don't see that option there, it's probably because you didn't select element force, L force as an output option, okay? All right. So what we're going to do here is we're going to look at the element forces. We're going to use all the components. So I'm going to just click apply, and that's going to color each element with its force, right? And so what you see here is this element has a force internal of it of 1.3 kips. And if you look at our solution, that's what we got. These here are about 2.67 type of thing, almost 2.7 kips, and that's pretty close to what we had before. I'll show you how to look exactly at those numbers, and then confirm that they're really spot on to what we had before. Okay, from the hand calculations. Now you'll notice that these two have the same force, and if you remember from the exact solution, they had the same magnitude, but this one's in compression and this one's in tension. And that's because when Hyperview is plotting the forces, it does the absolute value. Okay, you can actually get the sign value on those and just confirm that. Okay, the easiest way to see that this one is in tension and the other two are, I'm sorry, that this strut is in compression and the other two are in tension, is we can actually look at the stresses. So instead of plotting the element forces, let's plot the element stresses, which are down here, and hit apply. And now you can see here are the stresses. So on these two back ones, we have roughly the same stress, like pretty much the 23 KSI, which is the allowable stress. Those are the elements we designed to, except you'll see this one's in compression, negative, and this one's in tension, it's positive value. As well as this one has a stress of about 17 or so. That's what we expect to see, okay? All right. The other thing we can look at is we can look at the model deformed. And to do that, we're going to click this little icon here. It looks like a deformed sort of weirdo beam. And if I click on that, it allows me to scale the results by the displacement. You can apply that. You won't see much because it doesn't move too much. The displacements are small, but we could scale that up by changing the value from here from 1 to about 5. And I think if we do that, you'll see the results. Okay, you won't see the results yet because I have to slide this slide over and then let that go. Okay, so you can actually animate this. If I click this button, and you can see that's the deformation, right? And you can see as it goes through the animation, this slider goes through. So if you don't see any deformation, make sure that this slider button is all the way to the right. All right, so there it's deformed. That seems to make sense. Okay, that's good. But you know, it's one thing to look at the values, but we really want to see the exact numbers, okay? To make sure, see how close our hand calculations were to the final element results. So let's go back and let's confirm the element forces, right? So let's go and change the contours to the element forces again from the element stresses. So we're going to go back here, click the little colored flag looking thing, and change it to element forces, and then apply. And now we're back to that. But I want to get the actual numbers, not just kind of guess at them through the legend bar, right? So to do that, there's this icon here. It's query. Okay, so we're going to click on query, and that's going to show you quantities of the elements that are shown. So the first thing is going to give you an element ID, and we can click these other things. What I want to do is scroll down here and have it put out the value of the contour plot right there. Okay, and I think that'll do it, right? Yeah. So now if I click this first element, there it goes. It says that's element 1, and it puts the value for the element for us, and you can see that is 1,365, which is pretty much exactly what we did by the hand calculation. Then we can pick this one, and again, that gives us the exact value we get by the hand calculation. And finally, the last one, and that one also gets the exact value, just without the sign, right? But you can check the sign by the stress being negative, so you know that's in compression. And now you can't select the rigid element because the rigid element doesn't deform, and if it doesn't deform, there's no strain, and if there's no strain, there's no stress. So rigid elements can't have stresses, right? If we want to look at the stresses in the wing, we have to model the wing separately, okay? And we'll talk about how to model wings and finite elements later on in the class. All right, so there you go. So we've done our first finite element model. We made it out of these C-rod elements, right? We've made the model by defining material, the properties of the C-rod elements, and then the elements, applied boundary conditions, done a load step, solved it, and now we've looked at the results, and in this case, we get pretty much exact, because the finite element formulation really is exactly the same engineering physics assumptions as the hand calculation. So that's why we get that such good comparison. Okay, we won't always get that, but this is what you should get. Okay, it's not surprising. All right, so that's it. I will stop the video here, and like I said, if you got lost a little bit, you can always back up and try to go more slowly over the steps. If there's something you can't figure out that I did, you can just ask in class or send me a message, okay? All right.